I had suggested, after defining the notion of position and then displacement, velocity, and acceleration, that ultimately I would put them together in different ways and arrive at three equations. That over here on the right-hand side of the board, as is tradition, that I would only have three equations that I could use to solve any problem of kinematics. That is, any problem that relates position, velocity, and acceleration in the case where the acceleration is constant. So I'm limited in the kinds of problems that I can solve, but as it turns out, there's plenty of great problems that I can do using just these three equations. Now, we've already seen some examples of problems that are quite easy to solve. That is, you're given some quantities, position, velocity, acceleration, whatever, and getting the answer simply involves plugging them into the equation and getting a result, so-called plug-and-chug problems. But naturally, those are not the kind of problems that I'm interested in. I'm interested in more sophisticated problems, and indeed, I'm interested in solving problems that I would not otherwise easily get an answer to. So, some more complicated, more sophisticated problems are coming. It's sort of the joy of doing physics. What I need to do for you today is very simple. I need to demonstrate for you a procedure that we'll follow to make it as easy as possible for us to solve problems of one-dimensional kinematics. The reason why is that just if I read a problem flat out, it may be complicated in order to understand how these relationships that I've derived apply to the problem that I'm trying to solve. So it's important that I go about it in an organized way. So I have a prescription for you for how to go about problems in an organized way, but because you're students, I'm going to require that you follow the precision. I'd like to give you a little heads up whenever I'm doing a thing that is a skill that you are going to be expected to have. And that's exactly what I'm doing today, demonstrating a skill that you are expected to have. Now, right off the bat, you're going to find it challenging to do, but after some practice, you should find it easier and easier to execute this particular scheme. First of all, I need a problem to solve today, a problem that involves position, velocity, and acceleration. Very often we refer to these type of problems as word problems because a scenario is described in a paragraph and we read that scenario and extract the important information from it and apply what we've learned to come to some result. So ultimately that's what I'm doing. Here's my scenario for the problem that I'd like to solve today. Imagine that you're traveling down a darkened road late at night, and so here I draw a car. This is my standard physics car that I draw all the time. Doesn't really look like a car, but give it a try. And my car is traveling along the road at a rather high rate of speed, 20 meters per second. That's a good clip to be driving along at. When all of a sudden, there is a deer in the road. Sort of course, a hazardous situation. Hitting the deer is catastrophic. I don't want that to happen. So here's the deer. I'll just get a little stick figure deer here. Deer's not paying attention either. This deer is 95 meters away. So the position of this deer here is 95 meters. And now I'm a little concerned. So I'm going to just make a note there, 95 meters. I'm a bit concerned. Am I going to hit this deer? No, you don't think so? Let's find out how it works out, shall we? Because as it happens, I know my car, from some experiments that I've done previously, has an acceleration that's equal to 2 meters per second squared. That's the best my car can do, speeding up or slowing down. It turns out if you did a real experiment on a real car, it would have a different acceleration speeding up than it would slowing down. That's perfectly fine. I'm just saying that the acceleration that I'm given in this problem is 2 meters per second squared. Now, this is the situation that I want to solve. I have lots of questions. Do I hit the deer? How far does the car travel before coming to a stop? How much time does it take for the car to stop? There are a lot of questions here. A lot of information that I don't know that I'd like to find out. When we have these questions asked to us in a homework assignment or on a test, very often we're asked to find one specific thing. Here, I'm just going to find out everything that I possibly can for educational purposes. Here is my strategy. It begins with drawing a picture that shows the physical situation that I'm trying to solve. You will be required to draw a picture. And I know that your art skills may not be great, but don't worry, I've seen the worst. Draw a picture showing everything that's going on the way that I've done here. Second thing I need to do is choose a coordinate system. My entire description of the universe began with choosing a place that is zero and choosing a positive direction. And then I drew out a number line with tick marks. I don't need the number line. I don't need to draw a number line on my diagram. That would be terrible. But I do need to choose the coordinate system in which I solve the problem, and I have to declare it, and this is the way I do. I choose where the car is at the beginning of the problem to be 0. That choice is completely arbitrary. You can choose 0 to be wherever you like. It makes no difference at all. But you have to choose. It's kind of funny that way. The choice itself makes no difference, but you have to choose. And so I choose that location to be 0. You could choose where the deer is to be 0. You could choose somewhere else to be 0. It turns out that although you can make any choice you like, some choices, as it happens, are smarter than others, right? Some choices of coordinate system can actually make it easier to solve the problem. But for this problem, I'm going to choose 0 to be there, and very sensibly, I'm going to choose that to be the positive direction. The direction the car is already traveling, and that's sensible. Why would I want to give the car a negative velocity for no reason? And as it happens in this problem, for the whole time that the car is traveling, it's going to be traveling in one direction. I might as well make it positive because negative numbers can give me a little bit of trouble. So I give it a positive velocity going in that, or positive, I call that direction positive, and so the displacement is positive, the velocity is positive. Getting the idea, this is actually a very simple problem, very straightforward. So I chose my coordinates, and I get points for making that choice. It has to appear on my diagram. So later on a quiz or on a test, I'm going to need to show the choice of coordinate system I use for solving the problem. Now that I know that, I need to understand what information that I'm given. And it's a bit tricky because every quantity in the problem has units, and the units all have to be correct. Now, I'm not terribly concerned, talking about physics, I'm not terribly concerned about teaching about units or testing about units. But it's really important that everything has to be in meters and seconds in my kinematic problems. Every once in a while in a problem statement, I'll be given miles per hour, I'll be given something in centimeters, something like that. I need to convert to meters and seconds. Good practice. Also, some of the quantities that appear on my list could be positive or negative because the position, velocity, and acceleration, these are all vector quantities. And so they can have signs associated with them. I'm going to be careful about that. Also, it's really important, sometimes when I read a problem of physics, things are explicitly stated. The time is 5 seconds. I got it. The time is 5 seconds. So you have that. That's good. Other times, there are quantities that are implied by the problem. They're not explicitly stated. And it's up to you to infer what the quantity should be. That is a tricky part. Here's the thing that is critically important and difficult to get you to understand, difficult to sell. The best physics problems, which are the ones that I want you to be able to solve, always involve thinking. We are transcending plug and chug here. There's always going to be a bit of thinking involved. And you know that if I say that I value that, then I value your ability to actually go ahead and do that, to think about the problem. This problem is going to require a little bit of thinking. In order to get myself organized when doing a kinematic problem, I'm going to make a list of the quantities that matter. The quantities that matter are the quantities that appear in the 3 equations written on the right-hand side of the board. And so I'm going to write my list: initial position, initial velocity, final velocity, time, and acceleration. This is my list of quantities that appear in the equations. I do not care about the color of the car. I do not care about the day of the week. I do not care about even the road conditions. I do not care about the species of deer. None of that is included. Now, there are some things that I'm not including that you might say are important. For example, I'm not including air resistance. As the car moves along, it's subject to a resistive influence of air. I am not including that in my analysis. Does it matter? Often. Does it matter in this case? I'm not sure. But point is, my analysis is imperfect. My analysis is kinematic. My analysis is approximate. Very often, that's the game that I'm playing. I also am not including the idea that if the car hits the deer is going to influence the motion of the car. I'm not going to consider that either. I can. But for this simple analysis, I'm not including any of that. The only thing that matters is position, velocity, time, and acceleration, and so I make my list. Here's how I proceed. I start at the top of the list, and I ask myself very honestly, do I know this quantity? And if I do, then I write down that quantity with the appropriate sign and the appropriate units right there on my list. If I don't know it, then I put a question mark. Students often go wrong here. They don't know a quantity, but they really want to. So they just sort of make up a number and put it. You can't do that. You either know a quantity or you don't. And if you don't know a quantity, that's fine. There's going to be some things that are unknown about the problem. So starting from the top of the list, here we go. Do I know the initial position of the car? Yeah, actually, it's an absurd question because I chose the initial position of the car. I chose it. And so very often I choose my coordinate system so that that initial position of the car works out to be 0 meters. I choose it that way. The initial position of the car works out to be 0 meters. It's a good choice. Here's where things get a little dicey. Do I know the final position of this car, which has spotted a deer and is trying to stop? Do I know the final position of the car? No, I see people shaking their heads no. Good for you, because the number 95 meters is written up there on my diagram. You have to avoid the impulse to just take that 95 and jam it in wherever. Grit your teeth and hope it works out, because that's not the way physics works. Here, I do not know where the car ends up. So the problem, you could say that the problem contains extraneous information. That's not actually true, because I'm going to solve for the final position of the car. If the final position of the car is beyond the position of the deer, not good for the deer. If the final position is ahead of the position of the deer, then deer is safe, but we don't know yet. Well, then I guess the deer is there, and the car's it's probably safe if the car stops just at the deer. So we're going to find out what happens. Do I know the initial velocity of the car? Well, yeah, it's given in the problem. That's explicit information. A car is traveling at 20 meters per second at the start of the problem, and so that's the initial velocity, 20 meters per second. Do I know the final velocity of this car, which is trying to stop after having spotted a deer? Yeah, I'm trying to stop. So if I'm trying to stop, I'm going to make the velocity of the car go to zero. Nowhere was that explicitly said, but it's implied. If a car is trying to stop, then you're trying to make the final velocity of the car zero. It's implied. That's me thinking in a physics problem. Thinking about what the objective is, what I'm trying to do, and filling out my list accordingly. How much time does it take the car to stop? I'm not told. I'm not told how much time. It's an unknown quantity, question mark. I'm going to give you a little warning in advance. Be careful. What is the acceleration of the car? What should I put on the list? Negative 2 meters per second squared. Negative 2 meters per second squared. The problem statement tells me that the car is capable of an acceleration whose magnitude is 2 meters per second squared. That just tells me the amount of acceleration that's possible. But when I put the acceleration on the list, I have to think. In order to slow, I need the acceleration of the car to be negative. Not because negative acceleration means slowing down. No. Because negative acceleration means subtracting velocity in every instant in time, to make the velocity less and less and less and less in every instant in time. That's why that works out negative. And if I make this mistake here, then everything that happens afterward is going to go wrong. This list, which you are required to make, this list is where all of the physics happens. You could make an argument that what comes after this part of the process, what comes after making the list, is just math. You could make that argument. I don't like it. It creeps me out, because what's the point of math if I'm not solving a problem? But this is where the problem gets solved. So when we're busy doing problem solving, and often the case, someone says, Scheidly, I can't answer this question. They show me their notebook. I immediately look at the list, because that's where I'm going to find the problem. And I'll look at a list and I'll go, oh, negative. Oh, that you don't know that number and you wrote that you know it. Final velocity is not zero. That's where the problem is. The problem isn't in people's ability to do math. It's how they interpret the problem and write the list. So the list is critically important. From the list, well organized, I now know that I've got everything sorted out properly. I know what I know. I know what I don't know. I've got all the signs right and all the units are true and correct and appropriate. And now I can solve the problem. There is more than one way through a problem, particularly when you're trying to find everything. I could find the two unknowns on the list in any order. I could find the position first and then find the time, or I could find the time first and then find the position. There also is more to be learned here than just the unknowns on the list. For educational purposes, I'm going to solve this problem in such a way that I find the time first. The time is unknown, so the question that I have is, how long does it take the car to stop? So, in order to solve that, I have to pick one of the three equations. And students often say to me, I don't know which equation to pick. Pick one. Any one. Just pick one. If you choose the wrong equation, and your list is correct, if you choose the wrong equation, it will become immediately obvious, because you'll write it down, you'll put numbers into it and go, wait, I can't solve for the thing that I'm looking for. Watch as I demonstrate. I'd like to know the amount of time it takes to stop the car. And I've used this equation in a lot of my homework problems, so I'm going to use v squared is equal to v naught squared plus 2a delta x. It doesn't have the time in it. How can I find the time using an equation that doesn't have time in it? Bad choice. Oh no. What do I do now? Choose one of the other equations? Oh, but this second one, x is equal to x naught plus v0 t plus 1 half at squared, it scares me. It's scary. It's got squares in it. All right, fine. I'll choose to solve the problem using the first equation. V is equal to V0 plus AT. And I write that equation down. I write it. V is equal to V0 plus AT. I write that equation down, and I'm required to, so that my physics teacher who's grading it can see what it is that I'm doing. So I just write the equation in standard form, and now I can start working with it and doing what honestly is using my math skills to find out what the time is. I can look at my list to draw any quantity that I need to put in this equation, and look, the final velocity is equal to 0. So I like to strike it out right off the bat. It's equal to 0. It's kind of special that way. But otherwise, I don't like to plug numbers in right away. I find that students often do. I like to jam numbers in as early as possible, turn it into an equation of numbers. I don't like that. I like to do algebra. And then when I get to the end of the algebra, then plug numbers in. It turns out that I'm right about that, because if I do the algebra, things may cancel along the way, and I may be doing fewer calculations in the end because I did the algebra to solve for the unknown quantity. The fewer calculations that I do on my calculator, the less my chance of making a mistake, because I'm minimizing the number of buttons that I press. So I'm going to do a little bit of algebra here. I'm going to subtract V naught to the other side of the equation. So negative V naught is equal to the acceleration times time. And then I'm going to solve for time, such that the time is equal to negative the initial velocity divided by the acceleration. And Scheidly, the time's going to work out negative. No, it's not, because the acceleration is negative. The negative sign that appears in this equation is going to be canceled by the negative acceleration. It's a little tip, a little utility to you, the physics problem solver. If you solve for the time and the time turns out negative, you've made a mistake, because time can't be negative. So when I put these quantities in here, I have the initial velocity. I'll put in my initial velocity was given is negative 20 divided by, notice I'm not putting units. I don't put in intermediate units. Someone on the internet is going to say that I'm a bad person because I don't put in intermediate units. I know what the units of the quantity are. I've already gone through all of that trouble in making sure that my equation was dimensionally consistent, and all of that's done. But I will put the units on my final answer. I've harped on that. Obviously, negative 20 divided by negative 2 is 10 seconds. I've discovered that it takes 10 seconds for the car to stop. It takes 10 seconds for the car to stop. That doesn't really answer the question that's on everyone's mind, and that is, does the deer survive? In order to know whether the deer survives or not, I have to solve this situation for the final position. If the final position of the car is greater than 95 meters, then the deer's in trouble. If it's less than 95 meters, then the deer is safe. Here I go to solve. I need to choose an equation. Well, I've just found the time, which means using the second equation is perfectly legitimate. Now, right now, someone could shoot up a hand and say, yeah, but you could use the third equation too. You're correct. I could use the third equation. Not gonna for instructional purposes, but I could. So there's more than one way to solve through this kinematic problem. The final position is equal to the initial position plus the initial velocity times time, plus 1/2 of the acceleration multiplied by the time squared. A little caution, please, when plugging numbers into the equation. First off, the initial position is equal to 0. I chose it to be 0. So on my list, the initial position is 0. The initial velocity, 20 meters per second, multiplied by the time, which is 10 meters per second, minus. Scheidly, why are you putting a minus? Because the acceleration is negative. That's going to make this second quantity here negative, because the acceleration is negative. 1/2 of 2, the negative 2, the negative sign's out in front there, times 10 squared. Well, I'm sorry. This is a little bit sad. 2 times 20 is 200. 1/2 of 2 is 1 times 10 squared is 100. 200 minus 100 is 100 meters. 100 meters is the distance that it takes the car to stop. And unfortunately, the deer is standing at 95 meters, and so this car is going to reach the deer. I have the luxury of doing that in textbook problems. It always works out happy in textbook problems. Always safe. If I make problems up, it not necessarily work out so well for them. But don't worry. There's also viscous drag of the air resistance, so the car will actually stop soon. So maybe the deer is safe. I don't know. This theoretical prediction of the behavior of a physical system is not necessarily the actual prediction of what will happen in nature. By the way, how did I know this velocity? What is the uncertainty in the velocity? What is the uncertainty in the acceleration? And therefore, what is the uncertainty in the... So this is a theoretical solution to a real and practical problem. And so the practical solution turns out to be much, much more challenging. I have to find new ways of solving problems to get better answers. So it's 100 meters. Now here's a question, a final question, because I'd like to have something where I use all 3 equations. That'd be super. A final question. When the car reaches the deer, how fast is the car traveling? Maybe the velocity is not that high, and it'll work out okay. So let me find out. I want to discover what is the velocity of the car when it reaches the deer. Sure, the car stops thereafter. That's true. So now I have to rethink. Solving physics problems involves careful thinking. So I'm going to use the third equation on my list, that the final velocity squared is equal to the initial velocity squared plus 2a delta x. The final velocity is now not 0. It was 0 previously, so I have to be thinking. I have to be heads up. I've kind of gone off piste here from the list. I've deviated. I have to keep thinking as I solve the problem. Because the final velocity is now not equal to 0. It's what I'm looking for. The initial velocity is 20 meters per second. Let me start to fill these numbers in. The initial velocity is 20 meters per second, which I'm squaring. Again, that acceleration is negative 2 times the displacement. Now the final position is different. Sure, if I want to skid to a stop, I go 100 meters. Sure, if I want to skid to a stop, I go 100 meters. But I now want to know what is the velocity when I reach 95 meters. So my initial position is 0. My final position is 95. Therefore, my displacement, 95 minus 0, is 95 meters. So I want to find what is my velocity when I reach that point. Well, 200 squared is 400. And now I've got, So 200 squared is 400. So now I've got, what? Sorry, I misspoke. 20 squared is 400. And I've got 100, 2 times 190. What's this work out to be? 380. And so my answer here is 20, but I got to be careful. That's 20 meters squared per second squared. The velocity then is equal to the square root of 20. And what is the square root of 20? Square root of 20 is what? So while it's true that when the car arrives at the deer, it's still moving. It's not moving that fast. Maybe it'll be okay. I don't know. What's that? It's not really that fast. So here, the important critical thing is this, just a little bit of a review. I have these 3 kinematic equations that relate position, velocity, and acceleration. In order to solve a problem, I draw a picture of it to give me a feel for what's going on, and then I choose my coordinates. That means choosing 0 and choosing the direction that's positive. That choice, completely arbitrary, but I must make that choice. Because the very next thing that I do is I make a list of all of the known quantities. I take care. Correct units, positives, negatives, and be on the lookout for implied information that I can add to my list. Sometimes I don't know a quantity, and that's fine. When I don't know, I put a question mark. And then to resolve whatever the question is, for example, finding the unknowns on the list, I apply my kinematic equations and solve, and then rationalize my answer. Think about it. Does that answer make sense? The question that was asked.